Assalamu alaikum. My name is Asma Bashar and my student ID is 210050670004. Today I am going to present a very exciting and innovative topic in material science, self-healing polymers. These advanced materials are designed to automatically repair and damage they undergo without the need for human interventions. Just like human skin heals itself after a cut, these polymers restore their structure and function after being damaged. Introduction. Let's begin by understanding what self-healing polymers are. These are the synthetic materials that mimic natural healing processes. They can detect what damage occurs, activate a healing response, and restore their functionality on their own. This unique ability to self-repair makes them ideal for extending the life and reliability of materials used in harsh or demanding environments. Key characteristics: damage detection, healing response, and restoration of functionality. Motivation. Now, why do we need these polymers? Conventional materials degrade over time, whether it's due to mechanical stress, fatigue, or exposure to the environment. Repairing them is often time consuming, expensive, and even impossible, especially in remote or extreme environments like deep oceans or outer space. Self healing polymers are developed to overcome these limitations by autonomously restoring mechanical integrity and functional performance, helping to reduce maintenance cost and increase durability. Historical background. The concept of self healing polymers has an interesting origin. It was first proposed in 1990s, inspired by the biological healing system. In 2001, scientist White and his team at the University of Illinois made a major breakthrough by developing the first autonomic self-healing material using microencapsulation technology. Then between 2005 and 2010, more advanced systems like vascular networks and intrinsic healing systems were developed. Today, researchers are focusing on creating multifunctional bio-based and smart self-healing polymers for a wide range of industrial applications. Classification. Self-healing polymers are categorized into two main types: extrinsic and intrinsic systems. Extrinsic systems have healing agents embedded in the polymer. When damage occurs, these agents are released and repair the material. Intrinsic self-healing polymers. Intrinsic systems, on the other hand, rely on the polymer's own reversible chemical bonds and chain mobility. These systems don't require any additional healing agent and can often be reduced or recycled. Extrinsic mechanism of self-healing polymers. First one method is microcapsule based system. Let's talk about the first extrinsic mechanism, microcapsule based system. Here the healing agent is encapsulated in tiny microcapsules. When a crack forms, the capsules break open and release the healing agent into the damaged area. It then reacts with a catalyst to polymerize and fill the crack. The healing agent is usually dicyclopentadiene. The catalyst used is Grubbs catalyst, and the capsule shell is made of urea formaldehyde. However, this system has some limitations. It allows only one-time healing and it may not be efficient for large-scale damage. The second extrinsic system is the vascular network. Here, a network of microchannels is embedded within the polymer. These channels act like artificial blood vessels, continuously supplying healing agents to the damaged area. The major advantage is that it allows for multiple healing cycles. It also offers greater healing efficiency. This method is especially useful in aerospace, composites, and structural materials where repeated damage and repair cycles are expected. Intrinsic self-healing mechanism. Now moving to intrinsic self-healing mechanism or systems. These materials rely on reversible chemical bonds that break under stress and reform to heal the damage. Some common types are Diels-Alder reaction. These are the thermoreversible covalent bonds that break and reform with temperature changes. Disulfide bonds. These bonds can reform under heat or light, making them ideal for rubber and gels. Hydrogen bonds. Although non-covalent, they enable healing through chain reorganization. Dynamic polymer networks. These polymers can rearrange their molecular structure and self-repair in response to stimuli like heat, light, or pH changes. Examples include vitrimers and supramolecular polymers. Healing activation triggers. Heat exchange. Its mechanism is enhances chain mobility or triggers bond reformation. For example, disulfide exchange, Diels-Alder reaction. Light. It breaks or reform specific light sensitive bonds. For example, spiropyrin based self-healing polymers. pH change. It alters ionization state of polymer groups. For example, polyelectrolyte based self-healing polymers. Moisture. It promotes hydrogen bonding or swelling. For example, hydrogel based self-healing polymers. Mechanical stress. It initiates mechanochemical reactions. For example, mechanophores. Key chemical systems. Let's now understand how these chemical systems are activated. Diels-Alder cycloaddition involves a reaction between furan and maleimide. When heated to around 100 degrees Celsius, the bonds break and can reform on cooling. Disulfide exchange reactions work under oxidative or thermal conditions. These are useful in reprocessable rubber and gel. Supramolecular polymers use non-covalent interaction like hydrogen bonding or host gas chemistry. For example, UP dimers form strong reversible link that allows the material to heal repeatedly. Applications. Self-healing polymers have a wide range of applications. In aerospace and automotive, they are used in structural composites, tires, and fuel lines, as well as in anti-corrosion coatings. In electronics, they are used in flexible and wearable electronics and self-repairing circuits, which increases the durability of devices. In medicine, self-healing hydrogels are used for wound dressing, tissue scaffold, and drug delivery systems. In construction, they are used in crack healing concrete and sealants, reducing the need for frequent repair and extending service life. Advantages and challenges. These materials offer several advantages. They reduce downtime and failure risk, improve sustainability, and support a circular economy. However, there are also challenges. Manufacturing scalability is still a hurdle. The cost of functional components is high, and it's difficult to ensure compatibility with existing industrial materials. Moreover, the speed and completeness of healing are still under research. Recent advances. Recent advances in this field have opened exciting new possibilities. 3D printable self-healing polymers. These allow for custom designed healing structures. Conductive self-healing polymers. These can repair both mechanical and electrical damages. Bio-based self-healing polymers. They use natural ingredients like lignin and chitosan, making them eco-friendly. Smart diagnostics. Integration of sensors to detect damage and activate healing is become a reality. Future directions. Looking to the future, research is focusing on scalable production methods that are cost effective, multifunctional materials that combine healing with conductivity, strength, or biodegradability, autonomous monitoring systems that sense and respond to damage in real time, and medical integration such as smart implants, tissues engineering, and automated wound healing materials. Conclusion. To conclude, self-healing polymers represent a revolutionary shift in material science. They significantly increase the lifespan of materials, reduce the environmental impact, and open up new possibilities for sustainable and intelligent material design. Ongoing research is continuously expanding their potential in diverse industries. Thank you.